Let's talk about molarity and solution stoichiometry. So molarity, you learned in that learning activity yesterday that the equation for this is molarity, which is going to be your big M, is going to be the moles of solute over the liters of solution. So remember, solute is the thing that is in the solution. So like your sugar, your Kool-Aid, your, lemonade, right? The thing that's actually being dissolved. And then the liters of solution, and this is important, it's solution, it's not solvent on the bottom. So this is the solute plus the solvent. That's what your solution is. So that last question on the learning activity, when you do this in the lab, you add the solute first and then you fill it up to whatever volume you're going to be at, because the solute will take up some volume as well. So that's your equation. And let's do an example. We have what is the molarity of a solution made by dissolving 324 grams of sodium chloride into enough water to make a 2.3 liter solution? So first and foremost, I'm given grams, right? So I'm given a mass of sodium chloride. So that's 324 grams of NaCl. And then into enough water to make a 2.3 liter solution. So my volume here is 2.3 liters. Now I know the molarity is going to be the moles of solute over liters of solution. So I shouldn't put M. Remember, moles is N over volume. So I need to change this mass into moles. Now the way to do that is that we have to look at a periodic table. And I do not remember the molar mass of sodium and chloride off the top of my head. So I'm just going to look at a periodic table. Of course, you could just Google molar mass of sodium chloride. That would be fine too. But we're doing it the old school way. This is what I want. All right. Oh my God, that's way too small. Okay, I can't see it. Let's go back. I got to go to my trusty P table. What am I thinking? Did I pass it? There it is. Sorry if I sound a little sick. I feel a little bit under the weather today. Okay, sodium, 22.99, so about 23. And then chlorine is 35.45. So our molar mass is going to be 23 plus 35.45. So about 35.5, which is 58.5, I hope, grams per mole. I'm terrible at doing math in my head. So now that we have our molar mass, we can convert to moles. So 324 grams of NaCl, and then I'm going to divide by 58.5 grams per mole. And so we end up getting 324, let me just do the math, 324 divided by 58.5, and we get 5.54 moles NaCl. So to find the molarity, it's just going to be that 5.54 moles over 2.3 liters of solution. So dividing this number by 2.3, and we get 2.4. I'm saying 2 and I'm writing 3. My goodness, it's early in the morning. 2.4 molar. So that's how you say that. You don't say the molarity is 2.4. You say it like 2.4 molar solution. And what this really is it's like a concentration, right? So the higher the molarity of the solution, the more moles of solute you have dissolved per liters of solution. Of course, we talked about how when we have a concentrated solution versus a dilute solution, there's no like threshold, like all of a sudden, okay, when I have this many moles of solute dissolved per liter of solution, it's a concentrated solution. No, this is like a relative term, right? You have to have two solutions to say one is more concentrated than the other. But here, what we're getting for molarity is we're getting a concentration, all right? So something that has a larger molarity is going to be a more concentrated solution, if that makes sense. So here's the math. All right, let's do another example. So example number 2, what is the molarity of a solution made by dissolving 23 grams of NaCl in enough water to make a 40 milliliters solution? So pause the video, try to do this one yourself before you watch me do it, all right? And then I hope you paused it. So now we want to know, again, the molarity of the solution. So I'm looking for molarity. And I know that I'm going to dissolve 23 grams of NaCl in enough water. So my mass is 23 grams. Again, we want to convert that to moles. So using the same molar mass as before, that was at 58.5, because again, this is NaCl also. So 58.5 grams per 1 mole of NaCl. So 23 divided by 58.5, we get about 0.4 moles. And then it says 40 milliliters. Now, milliliters, you want to convert to liters in this case. We do not want milliliters in our equation. It is liters of solution. So 40 milliliters, we want to divide that by 1,000 because there are 1,000 milliliters in 1 liter. So what we end up getting is 0.04. And then again, to find the molarity, it's going to be your number of moles, so 0.4 moles of solute over 0.04 liters. So 0.4 divided by 0.04, and we get 10 molar. Okay, so that is our molarity of the solution. I just rounded a little differently when I did it before. All right, let's talk about percent mass. So percent mass has to do with mass. Now, usually when you see mass, you immediately convert to moles, but in this case, it's a little different because we actually want mass. So your percent by mass is going to be the mass of the solute over the mass of the solution, all right? And then, of course, multiplying by 100 because this is a percent. So for example, if I have 324 grams of sugar dissolved in 1 liter of water, what is the percent mass? And then I give you the kind of density of water. Well, I just give you that 1 milliliter of water is 1 gram. And that is because of the density of water. And remember, this is only for water. You can't use this for any other solution because the density of water is 1 gram per milliliter. So what this tells us is that if I have 1 liter of water, that is 1,000 milliliters of water, which then is 1,000 grams. So my mass of water is 1,000 grams in this case. And then I know that I have 324 grams of sugar. So 324 grams of sugar. Now, you might be thinking, well, what sugar is this? You know, what is the chemical formula of sugar? But in this case, because we're using the percent mass, I specifically ask for percent mass, you actually don't have to convert it. You would need the chemical formula if you need to convert it to moles, but we're not finding the molarity, so we don't need to convert to moles. So what we need is the mass of the solute, which is going to be the sugar, so 324 grams, over the mass of the solution. And remember, this is the solution. This is not the solvent, which is just water. So because it's the mass of the solution, it's going to be both of these things together. So what we end up getting is 324 grams divided by 1,000 plus 324 grams. Because again, this is the mass of the solution. This is both of them together. Once they're mixed together, the solute and the solvent, that will be the solution. All right, so times 100. And then doing the math here, we get 324 divided by 1,324. And then I don't divide. 324 divided by 1,324 times 100, and we end up getting 24.5%. That is our percent mass. Now let's do another example. What is the percent mass of a solution containing 134 grams of lead nitrate and 266 grams of water? So again, pause the video, try to do this one yourself. Now that you've unpaused, let's do it together. So my solute in this case is that 134 grams of lead nitrate, and then my solvent is the 266. The solution together is going to be those two things added together. So we have solvent on top, 134 grams, over 266 plus 134 grams, and then times 100. And so on the bottom there, I have 400. So that's 134 divided by 400 times 100, and we get 33.5%. All right, easy peasy. All right, let's talk about solution stoichiometry. You're not done with stoichiometry yet. So remember, in stoichiometry, when we have a chemical reaction, in order to convert from one thing to another, we need moles. That's the main gist. When we talked about gas stoichiometry, if you had like a pressure and a volume and stuff like that, then you have to use the ideal gas law, PV equals nRT, to find N, because that's your number of moles, right? And that's how you related those variables together. Now, in this case, we're talking about solution stoichiometry. So we're talking about molarity. And molarity is moles of solute over volume of solution. So you're going to use that molarity equation in order to get your moles to convert from one thing to another. And that's the main idea here. Okay. So molarity can be used as a conversion factor between moles and liters of solution. If I have a 5 molar solution, that means I have 5 moles for every 1 liter of solution. And so remember, in our conversion factors, in this case, that's 5 moles equals 1 liter. All right, and you can use that as a conversion factor. This is when I have a 5 molar solution. Okay. I just said that. So you can use this as a conversion factor, 5 moles over 1 liter or 1 liter over 5 moles, depending on what you have. And I'll show you what I mean in a second. If I have a 3.78 molar solution, that means I have 3.78 moles for every 1 liter of solution. And again, using it as a conversion factor, you have that. Okay, so example number 1, we have what volume of 2.5 molar zinc nitrate is needed to produce 1.8 grams of zinc ferrocyanide. So I have this 2.5 molar zinc nitrate, which is this right here. 2.5 molar is going to be the concentration of zinc nitrate, all right? So I can use this as a conversion factor like I had on the last slide. So that means that 1 liter of the solution equals 2.5 moles of zinc nitrate, all right? So 1 liter equals 2.5 moles of zinc nitrate. Okay, and so I can use that as a conversion factor. Now this is my given here. So I'm going to start with 1.8 grams of zinc ferrocyanide. So 1.8 grams of ZN2FeC6N6. And if that looks really intimidating, just know that you know what nitrate is. That's on our polyatomic ion sheet. So that FeC6N6, that has to be ferrocyanide, that polyatomic ion. So don't get intimidated about it. You're totally fine. So this is what we're starting with here. And I know that in order to convert from one thing in a chemical reaction to another thing, I need to convert to moles first. So the molar mass of zinc ferrocyanide, you of course get from the periodic table. I already did it right there. It's 342.6 grams per mole. So 342.6 grams per 1 mole of this. Now, in order to convert from one thing to another in a chemical reaction, we now have the mole ratio. So there's 1 mole of this to 2 moles of this. So 1 mole of zinc, and I'm just going to put Fe because I'm running out of room, to 2 moles of zinc nitrate. And then now that I have moles of zinc nitrate on the top, I now want to use my conversion factor here in order to convert from moles of zinc nitrate to volume of zinc nitrate. So moles go on the bottom because I want to cancel that out, 2.5 moles. And then the volume, 1 liter, goes on the top. And then now I have volume. So that's it. So grams of zinc nitrate cancel out, sorry, zinc ferrocyanide, moles of zinc ferrocyanide cancel out, moles of my zinc nitrate cancel out then as well. So now doing the math, we just get 1.8 times 2 on the top, and then I'm going to divide that by, open parentheses, 342.6 times 2.5, close parentheses, and I get my volume is equal to 0.0042 liters. Now, of course, this is a really small number, so you can convert that to milliliters if you would like to, which is 4.2 milliliters. Okay, so that is our answer. All right, let's do another one. So if 20.5 milliliters of 0.12 molar potassium ferrocyanide, so that is going to be this right here, and 15.8 milliliters of 0.2 molar zinc nitrate react, how many grams of zinc ferrocyanide is formed? Whew, okay, so this is a limiting reactant problem. And I know that because I'm given an amount of this and an amount of this, and I want to know how many grams of this is formed. All right. So because we're given the amounts of our two reactants, that means that one of them is going to be a limiting reactant. So what I'm going to do here is, because I'm given a volume and a molarity, I can find the number of moles from that. So I'm first going to find the number of moles that I have of potassium ferrocyanide reacting, and then the number of moles of zinc nitrate reacting. And then from that number of moles, I'm going to see how many grams of zinc ferrocyanide that's actually formed. So my molarity, I know molarity is equal to mole over liters, okay, or N over V if you want to put it like that. So for the first one, potassium ferrocyanide, I know that if I convert this equation to equal moles, it'll be moles equals molarity over, Mrs. Stewart, it's too early to do that. Moles is equal to molarity times volume. So moles equals molarity times liters. Okay, do you see what I did there? I was trying to do that in my head and it just didn't work. So I multiplied both sides by liters or volume. So we get the moles of the first one is going to be the molarity, which is 0.12 molar, times the volume, but of course we want the volume in liters, all right? So that means 20.5 milliliters. I have to divide that by 1,000. You can also just move the decimal. It is 0.0205 liters. And so that multiplied by 0.12 is going to be equal to 0.00246 moles of that potassium ferrocyanide. Doing the same thing for zinc nitrate, we get the moles of zinc nitrate equals the molarity, 0.2 molar, times the volume in liters. So 15.8 divided by 1,000 is 0.0158 liters. And then I'm going to multiply that by 0.2. And so I get 0.00316 moles of our zinc nitrate. All right. So now that I have our amounts in moles, I now can find how many grams of zinc ferrocyanide is formed. And so remember, I have to do two different calculations. And then because this is a limiting reactant problem, whatever is the lesser amount is going to be the amount that's actually formed. So starting with 0.00246 moles, and this is the first one, so potassium ferrocyanide, which is K for FeC6N6, C6N6. My goodness, I'm just running out of room constantly, I feel like. So we already have moles. Now I want to convert from moles of this to moles of our zinc ferrocyanide, which we can see that it's a 1-to-1 ratio, right? One of this forms one of this. So I'm just going to say, okay, 1 mole of KFe, I'm just abbreviating here because I'm running out of room, forms 1 mole of zinc ferrocyanide, so zinc Fe. And then, of course, I want my answer in grams because it says how many grams is formed. So now I want to use the molar mass, which luckily I found before and I don't have to do it again. Remember our molar mass was this one right here, 342.6 grams. So 1 mole of that zinc ferrocyanide is 342.6 grams. And so I have on the top 0.00246 times 342.6, and that's it, right? Because on the bottom I'm just dividing by 1 times 1. So I get 0.843-ish grams produced from that potassium ferrocyanide. And then I want to find how much would be produced from the zinc nitrate. So zinc nitrate was this 0.00316. So I have 0.00316 moles of zinc nitrate. And then I want to convert to moles of zinc ferrocyanide, so I can see that it's a 2-to-1 ratio. So 2 is going to go on the bottom, 2 moles. And then 1 mole of my zinc, again, that's abbreviated. And then I want to do the same thing that I did up here. I want to now convert to grams. So I get 342.6 grams to 1 mole of my zinc ferrocyanide. And so I get 0.00316 times 342.6. And then I'm going to divide that by 2. 0.00316 times 342.6, and then I'm going to divide that by 2, and so I get 0.541 grams produced from my zinc nitrate. So we can see here that this is going to be the amount produced because this is the limiting reactant, because less is produced when we have this much zinc nitrate. So remember, in limiting reactant problems, you want to pick the amount that is produced that is less when you do it like this. So my answer should be 0.54 grams, which is right here as well. All right, I'm going to actually leave this one because this video is long enough. You will see my answer here. And I can do a separate video if you're like, I have no idea what's going on, or we can do this as an example in class when I get back. But I don't want to make this video any longer than it already is. So good luck with your solution math worksheet. The answers are on Canvas already, so make sure you check your work as you go. When I get back tomorrow, I will be taking questions, all right? So make sure you put some stars by whatever you're having trouble with, and we will go over that together, all right? Good luck and good job, and I will see you later.